All right, so the context we're going to be looking at today, we're actually revisiting this. So we saw this first last week on Friday, the very first day that we were introduced to a log function. It's the context of duckweed. So we talked about the duckweed plant grows on top of water. Imagine like a small kind of lily pad type growth. And true fact that this plant multiplies very fast. In fact, the number of it doubles every day. And so a pond that has that type of plant can get completely covered in a short time. Makes the surface look like green grass. So when we looked at this originally, we were measuring our area in square meters of the pond that's covered by duckweed. And we're measuring time in days. And so when it has been 0 days, we saw that the original amount covered was 1 square meter. When 1 day passes, it doubles up to 2 square meters. After 2 days, it got up to 4 square meters. After 3 days, it went up to 8 square meters, and so on. So we saw this pattern that every day forward results in the duckweed doubling, or the duckweed multiplied by 2. And so we're going to take a look. We've seen this table before, but we're going to be using it again today. This table has the time in days. This is accurate out to 2 decimal places. For all of these areas, so starting with an area of 1 square meter all the way up to 26, notice how to meet all of these areas, it's not always the perfect whole number of days. So some of these are like fraction of days. So like at some point, like in between 1 day to the next, if we get into hours, we can kind of calculate about where that would be. But that's why some of our values here are decimals. So before we knew about the notation for a logarithm, we were using a different notation. Remember that we had this t function, and we had a little number in parentheses next to it, so like t of 24. We define that to be the time it takes the duckweed to grow to a size of 24 square meters. And the ending piece there is just a little bit more information about how the growth is happening. We're going to specify that that is when doubling. All right, so we have a definition here for the t of 24. So in question 1, so it's asking us how can we find t of 24 using t of 6 and t of 4? Well, let's take a look at where we can find information about these values in our table. So starting with t of 24, the time it takes to grow to a size of 24, well, we're going to be looking to see when the area is 24, and we can see that that is 4.58 days. So I might even just make a little note of that here. So that's the actual time period that that is describing. And then we want to take a look at t of 6, which is the time it takes to grow to a size of 6, which is 2.58 days. And then let's go ahead and find in the table t of 4. So that's how long does it take to get to an area of 4 square meters. And we can see that that is perfectly 2 days. All right, so I would like you to turn to the people that you are sitting with and tell them, is there anything you notice? Is there any connection between these values? The 2 values on the right-hand side, so we see 2.58 days plus 2 days is equal to 4.58 days. So we could write this off to the side in a different way, going back to that t notation, that t of 24 is equal to t of 6 plus t of 4. Now, I'm curious if you noticed anything else. Like, what is the relationship between 6 and 4 and 24? What's happening there, right? Yeah, they're just being multiplied. So when we multiply the 6 and 4, we get 24. All right, so using that, you are going to write 2 other relationships similar to what we wrote down in number 1. And once you have done that, I actually want you to finish through the questions on the first side of this paper. So I want you to work all the way through to the end of question 5. you can continue to utilize the information in the area time table to help you with all of those. If you have a different color with you close by, we are going to make a few notes about this off to the side. So this is actually the first property that we are going to look at today. So remember that when we very first learned about log notation, instead of using the T to represent the time it takes to grow to a certain size, we are using log base 2 of A, so A represents whatever the size is that it's growing to, and we know that the answer to that log is representing a time period. In this case, it's a time period in days. So to rewrite this, instead of saying it as T of 24, let's go ahead and write this as log base 2 of 24, so we still have the 24 represented in parentheses. The part out in front just looks different. And we saw that that was equal to the time it takes to grow to a size of 6. So we're going to write that as log base 2 of 6, plus the time it took to grow to a size of 4. And so we're going to write that as log base 2 of 4. So we see that the log expressions here on the right side are being added together. And then what happens here to the areas is that they were multiplied. 6 times 4 was equal to 24. So we're going to generalize this to write out a statement for this first property. And I'm just going to switch the order when we write this out here. I'm going to put the addition part listed first, and then the answer part at the end, but that's okay. It's just a different way of saying the same thing. So we're going to say here, I'm going to say log base B. So I'm going to do a little b there in place of the 2, just because it doesn't have to be log base 2. Technically, it could be any base. And then whatever it's being of, I'm just going to call that m. So really that m that could represent a number, like over here it's 6, plus log base b of n, that would be something else, is equal to log base b of m times n. And this property will work as long as the base is the same for these two pieces here on the left-hand side. So I'm not going to try to trick you. I'm not going to give you one where the base is not the same, but just know that in the world of the properties of log, like it has to be the same base, and when it gets condensed, to get this right-hand side, like the base is still the same as whatever it was. So the key thing to see here is when they're being added together, it's getting condensed, combined together through multiplication. All right, so let's take a look now at part 3. So number 3 here was asking us how we could find T of 5 using T of 20 and T of 4. So if we go ahead and find these values here, so here's the time it takes to grow to a size of 5, the time it takes to grow to a size of 20, and the time it takes to grow to a size of 4. All right, so it looks like here we have now a statement involving subtraction. And so sure enough, if we fill in the number of days underneath, 4.32 days minus 2 days is equal to 2.32 days. All right, so we're subtracting, and what's really going on between these values here? Like, what's the relationship between the 20, the 4, and 5? Did you guys notice? Or how could we get 5 from the 20 and the 4? Veronica? We're dividing them here, yeah, so instead of multiplication, like this whole statement is kind of the opposite of what we did before. So notice how 20 divided by 4 is equal to 5. All right, and there's other kinds of relationships similar to that we could have found in the table. We're going to go ahead and generalize this, again, off to the side, and we're going to put it into log form. So starting with the first statement here that I wrote in blue, this could really be written as log base 2 of 20, that still means the time it takes to grow to a size of 20, minus log base 2 of 4 equals log base 2 of 5. All right, now we had a base of 2, but it could have been any base. We had the values 20 and 4 and 5, but they could have been other values. And so to generalize this, we can say here that log base b of m minus log base b of n is equal to log base b of m divided by n. And I'm going to use the fraction division symbol here. Every fraction really means the numerator is being divided by the denominator. Now, here's something that we want to be really careful with this subtraction property that gets rewritten as division. Notice how when it is condensed on this right-hand side, we only write log one time out in front. So it is a single log in front, and the division is happening after it. A common mistake that students sometimes fall into is they accidentally write this property as log base b of m divided by log base b of n. Notice the difference here. There's a log on the top, and then there's a different log on the bottom. And it's actually going to lead to an entirely different result altogether. So if you did write that on your paper, that's okay, but you have to make sure you put a big X through it, because that's not the example that we want to follow. In fact, I'm going to show you an example here on the calculator for why that does not work. So if I were to find my log key here, I'm just going to make up some numbers. All I get is going to work out as a decimal. So I'm going to do log of 8 divided by 3. Now notice how if I do log 8 minus log 3 using my property, notice how it equals exactly the same thing. So that is a good way to condense it down. Here's what we don't want to do. If you type in log 8, close the parentheses, divide it by log 3, notice how there's 2 logs here. You get our answer? It is totally different. So if you're ever unsure of how something works with a property, try it with some numbers and see if it works out how you want it to. All right, so that is our second property. And there's one more that we are looking at here. In part 5, it wanted us to take a look at our table and verify that log base 2 of 9 is equal to 2 times log base 2 of 3. So let's take a look at that. So this first one here, this is just the time it takes to grow to a size of 9. So that is right here. It is 3.17 days. All right, we're going to see if that's equal to 2 times the time it takes to grow to a size of 3. Look at the time it takes to grow to a size of 3. That is 1.58. And here's the thing. When we do that multiplication, it is close. It's a little bit off, and that's only because of rounding. So that 1.58 answer is actually not exact. It has been rounded. The 3.17 days has also been rounded. But this is, it's so close, we can verify, yes, they are the same. It looks like it's, yes, approximately the same answer for the number of days. And so there's a little something special that's happening with this statement right here. So on the left-hand side, instead of writing this as log base 2 of 9, I could have written this as log base 2 of 3 squared, right? So notice how 3 squared is the same thing as 9. Well, then what happens when we're taking the log of something that is raised up to the power of an exponent, notice how in order to get this right-hand side, the position of the 2 that used to be the exponent up there, that 2 has now been moved out to the front. And all we have left is just to 3. So I'm just going to rewrite this down here. Another way that I like to kind of show this and write it is that if we have an exponent, like we'll put a little arrow here to show, then it's going to move out to the front. And all we're left with then is the base part that was originally holding up our exponent. So we're going to turn that into a general statement here. So one more property of log. It could be any base. It doesn't have to be a base of 2. So I'm going to write this as log base b of something that's holding up an exponent. So I'm going to write it as m raised up to the power of n. And then what happens is that exponent of n gets brought in front, and it's just going to multiply. We still have log base b of m behind it. All right, so we're going to summarize here. So our first learning target we had was to look at discovering what are those properties of logs. So I'm going to say here 3 properties of logs. So we are going to rewrite them here. So we have them all together in one place. So the first one we did here, log base b of m plus log base b of n, when they have the same base and they're being added, they are going to condense down using multiplication. So it's the same thing as log base b of m times n. All right, our second property, log base b of m minus log base b of n. When they're subtracting, it's going to condense down. It's just going to have a single log out in front. Do not write log twice. The log just happens once, and then the division happens after that. M divided by n. All right, and then our third property helps us with what to do if we're taking the log of something with an exponent. So log base b of m to the power of n, the exponent part, n, gets brought down, and it's going to be rewritten in front. Everything else stays the same. Once that exponent has been moved, it really just changes the division. Now let's just make a little note down here at the bottom that for property 1 and 2, we must have the same base in order for it to be condensed. And so by that I mean this little number down here where I wrote the b, that's what we call the base. It has to be the same thing, and when it's condensed, that condensed answer is just the same base as whatever it was. All right. Something that we didn't talk about yet on the front side, but is one of our learning targets for today, is to understand the meaning of the common log. I'm actually going to write the whole word out here. It's good to have a reminder of what do we really mean when we say the word log. It stands for logarithm. And the common logarithm is the log with base 10. And a log with base 10 is commonly used, hence the name common log. It's so commonly used that it is usually shown without showing the base. I'm getting confused on my words. It's usually shown without sorry, that got a little confusing. It's usually shown without the base. So here's an example. So let's say we wanted to describe log base 10 of 17. So base is what we're calling the little number down here below. Well, instead of writing the 10 there, we would just write log 17. So this is super helpful to tuck away in your mind and think about moving forward, because at any point in time now, into the future, if you see a log written and you don't have a little base that's shown, we're assuming that it's base 10. If it's not 10, it's going to be written there, but if you don't see it, you just need to remember it's 10. All right, so in our check for understanding, so this is going to help us actually with our third learning. Oh wait, no, go back to the top. So the first learning target, when it's talking about condensing and expanding expressions, well, that's really all that we're doing here. If we think back to like the first two properties that we wrote out, if you start with more logs and you condense it down to make something smaller or shorter, going this direction is condensing. But if we wanted to write it out and make it longer and expanding it out, that would be going the other direction. So that would be like starting with something on this side and then expanding it out to make it look like something on the other side. So we're going to look at a couple of these problems here together, and then I want to actually give you a chance to try some of these on your own. So in the first section here, we're going to be using properties of logs to condense these expressions. And I want to actually have us take a look together at part B, just because there's a few different things going on here. So one thing to notice is that we have a subtraction sign, so that should help us start to think about what property it's going to match with. But the other thing going on is we have some numbers that are out in front, and we want to deal with those numbers in front before we think about doing anything with the subtraction sign part. And so whenever we're condensing, if we see numbers in front, the first thing I want you to do is move those numbers in front. I want you to move them back up to the position of an exponent. So kind of like going backwards. So I'm going to write an in-between step here, log of y to the fourth minus log of 7 squared. And you can write 7 squared there, or you can write 49 and actually do 7 squared and get the value. All right, and then finally, because we have a subtraction sign, that's going to match with our property that involves division. We're only going to write log one time in front. The division happens afterwards. Whatever is listed first is going to go on the numerator part, and then whatever part is listed second goes on the denominator. Instead of putting 7 squared, I'm going to go ahead and write 49. That is our final answer. You don't have to do anything else with that. We're just rewriting this in a different form. Let's take a look at one of our examples in the expanding section. So notice that when we're expanding, all of these problems start with just a single log. Our goal is to write it out longer. We're going to expand it. We're going to take a look at part B on this one as well. So when we're expanding, first thing I want to look at here on the inside is, do I have multiplication or do I have division? So since I'm noticing here that there's multiplication happening, I'm going to first split this up using addition. So it's going to be the log of m squared plus the log of m to the fifth. Now, the last thing that we're going to do, when we are expanding, we're going to take these little exponents. We don't want to leave them as exponents. We're going to move them so that they go out in front. So the first one here, when that 2 goes in front, it's going to become 2 multiplied by the log of m. And for the second part here, that 5 is going to go in front of that part of 5 and the log of n. All right, so I'm going to put a little bit more time on the clock here. I want you guys to try to do the rest of these, or as many as you're able to. All right, so we're going to come back together. We're going to look back at part one to finish out our condensing. So in part A here, we don't have any special numbers in front that we need to think about dealing with, and so really we can just start right away looking at that plus sign. Now because they're being added, we're going to condense it down to a single log in front, and it's going to turn into the two pieces being multiplied. So that was really our first property that we did today. The 2 is going to get multiplied by x. You don't have to write the multiplication dot. You can, but you could have also just written 2x. And that's it. All right, in part C, we have a couple of things going on here because we see both an addition sign and a subtraction sign. So my suggestion for you on something like this is to condense it working from left to right. So I would say let's just first focus on like the first operation, the first thing we see happening, just looking at the plus sign part. So we can condense this down to be log of x times y. We're going to kind of think about doing this in pieces. Then the only thing we have left is to deal with the subtraction part, and we know that that's going to condense it down using division. So the entire x times y goes on the numerator because whatever's listed in this first position is always the top part of our fraction, and then whatever's listed in the second position is going to go on the denominator. And that is our final condensed answer there. And then we'll take a look down here at the other expanding problems. So starting here with part A, log of x divided by y, because it's division, we can expand it out using subtraction. So we're just going to split apart the numerator and denominator. We're just going to put a subtraction sign in between both parts. We have log x minus log y. Let's take a look here at part C. So it's not division that's happening. This is actually multiplication. So think about there being a little multiplication dot. And so initially we can split this up using addition. Separating out the 10 and then the square root x part. Now what's kind of interesting here is that this square root x is really the same thing as x to the 1/2. So remember with our square root symbol, we could write that as an exponent of the fraction, and the specific fraction that it is, if it's a square root, is 1/2. So if we think about moving that 1/2 out in front, which is what we normally do when we have an exponent, we do this when we're expanding. We want to try to move those exponents to the front. We can actually write it as 1/2 times log x. Now, actually, there's one more thing that we can do on this one. And it has to do with the part that we have listed out in front, the log 10. If you come across something that you can evaluate perfectly, then I want you to evaluate it. I want you to look out for that. We don't see a little base down here. So what is the base? Invisible. What is it doing? What is it? A little base. If you don't see the base, it's 10. Yep, that's the common log. Okay, so there's a little 10 down there. So let's think about what this is asking. Log base 10 of 10. Well, this is trying to figure out if we were to evaluate this. So we pretend like there's a little equal sign to a question mark here. This would be asking, starting as a little base, 10 raised up to what power equals 10? 1. That's right. So this whole part here, log base 10 of 10, that is actually 1. So I'm not going to write it using log at all. I'm just going to write it like this, equal to 1. You're not always going to be able to do that, but sometimes you can, so I want you to watch out for it. All right, and then finally here for part D, we have a couple of different things going on here because we have things multiplied together on the top being divided by something else on the bottom. It's actually kind of like part C of the previous piece, where we ended up with things multiplied on the top, divided by something on the bottom. So if you have that scenario, you want to think about splitting apart the fractions first. So think about splitting up the numerator from the denominator. And so to split apart that fraction, to split apart the division, we know that we need to use subtraction. So I'm going to do this one in a couple of steps as well. So I'm going to do log of the whole numerator minus log of the denominator. Then we can take this a step further. There's more that we can split on the numerator part, this part in front, because there are two different things here on the inside that are being multiplied. So we know that multiplication gets split up using addition. So it's going to be log of 2 plus log of x to the third. We still have minus log 5 at the end. And one more thing we can do. You see it? What else can we do here, Remy? Perfect. We only do this when we are expanding, but if you end up seeing anything that still has an exponent, we're going to move all of our exponents to the front. So the middle term becomes 3 log x. Everything else there stays the same. So a couple of steps there on that last one, but that would be our final expanded answer. All right, so I'm going to give you a few more minutes here to work, and I want you to take a look at and actually work through questions 1 through 4 on this second paper. And, okay, so let's take a look here at number 1. So we did some work with this in our very first lesson for logarithm, log base 2 of 8. And there's definitely a couple of ways you could have thought about this. Because it's base 2, it connects with the context of the duckweed plant that doubles every day. And so this is really asking how long does it take to grow to a size of 8? And we saw that it was 3 days. Another way that you can think about it is, okay, I'm going to start with a little 2 down here. 2 raised up to what power equals 8? In other words, we're solving for the exponent, and we get the same answer of 3. All right, log base 2 of 8 is 3. Now, in the second part here, we're going to grab our calculator. And even a scientific calculator will work on this. You should have noticed that there is a log key. On a graphic calculator, the log key is right next to the 7. And so when I press the log key and then I just type in 8 in the parentheses part, notice that we're not getting the same answer. We didn't get 3. And so really all that's telling us here is that, well, when we press that log key, this is not doing log base 2. It must be using a different base. That's the only explanation for why we're not getting the same answer. And so we wanted to try out some different scenarios to see what the base is that we're using instead. And so our paper has us do log 10, we're doing log 100, log 1,000, and the last one was log of 1/10. So based on the answers we're seeing here, does anyone have an idea of what the base, the calculator key, is actually using? What is it, Daniel? Base 10. Yeah, how do we know? Can you use one of these examples to explain? What did you notice here, Remy?
It's like if you what you did before, and you're like, oh, there's 10 to the power of what times 10, and look at that, that's what it's up to.
Try it. Yep. 10 to the power of 2 is 100. Yep. 10 to the power of 3 is 1,000. That works. 10 to the negative 1, remember if we have a negative exponent, it just turns it into a fraction. Yeah, so this is all base 10. And this is actually not too different from what we just talked about with the common log. Because look, when you press the log key, the base is not showing. And didn't we say that when we don't see the base, we're assuming that it's base 10. So that is the base that our calculator log key is using. All right, now something like log base 2 of 5. This would definitely be challenging to do without a calculator. Because we would have to figure out 2 raised up to some power is equal to 5. However, 5 is not in the family of the powers of 2, right? So if we do 2 squared, we get 4, but then if we do 2 to the 3rd power, we get 8. 5 is somewhere in there. It's not a whole number exponent value. It would be a exponent that maybe has a decimal in it, so somewhere between 2 and 3, but there's really no way exactly for us to just guess and figure out what that would be. So we're going to talk about, well, how could we do that on the calculator? So if we have something like log base 2 of 5, we know that we can't just press the log key, because that's base 10. Let's make a little note of that here. Log key on our calculator is base 10. It may seem that there's no way to have the calculator do the work for us when we have a different base, but there is. The way that we do it is using something called the change of base formula. And how the formula works for any base, the base can be changed to base 10 through a simple formula. So you'll notice here in the box here, so it's telling us that log base b of a is equal to log a divided by log b. Notice how on the part I just read, the base wasn't shown to us, and so it's assumed, it's implying that it's actually base 10. And if we can turn it into something that involves base 10, well then we can use our calculator log key. Now, a helpful way for us to remember where the values go, what position do they go in, on the top or the bottom, is that the little base part, we're going to call that B. Notice how that's the number that gets listed on the bottom. So I always think about that here. Base goes on the bottom, and they both start with the letter B. All right, so we're going to put the formula here to the test. We're going to see if this really works. And so I wanted to begin by giving you one that we're familiar with, because we already know the answer to log base 2 of 8 is supposed to be 3. So if we put it into the change of base formula, it's going to turn into log base 10 of 8 divided by log base 10 of 2. You don't have to write the base 10, but that's really what it is. We do need to be careful when we type this into our calculator, because when you press the log key, your calculator is going to give you this first parenthesis automatically. Well, after you type in an 8, you have to type in the second parenthesis before you divide. So let's take a look at that here on our calculator screen. So I'm going to find my log key. So this is really doing log base 10 of 8, close the parentheses, divided by log base 10 of 2. Formula works. We get the answer that we would expect to get, which was 3. Now the way for us to check this is to think about putting it back into exponential form. It does work because, sure enough, 2 to the power of 3 equals 8. All right, so let's go back to that log base 2 of 5. We talked about this a few minutes ago, and we said, yeah, that would be hard to do, just thinking about it. But let's put it into our formula. So it's going to become log base 10 of 5 divided by a log base 10 of 2. So here's what that looks like. You're in our calculator. Close the parenthesis around the 5. And sure enough, it is a decimal. It is between 2 and 3. We see that it's about 2.32. Now, a way for us to check that, let's actually write this here on paper. I'm going to round it out to 3 decimal places. If we do the loop here, we're going to start with the base of 2, and we're going to think about 2 raised up to the power of 2.322, and that should equal 5. If you rounded it, though, it's going to be close to 5. It'll be like approximately 5. So here's how we can check it here. If I use my rounded answer, 2.322, and like check that exponent, I get 5. Only reason it's a little off is because we rounded. All right, so I want you to try the next 2 on your own. So go ahead and try part D and E. When you get an answer, let's round it out to a few decimal places instead. And then I want you to also do that final step of checking to see if that really is that missing exponent that we were